right, so I'd like you to go ahead and take a minute and look at these two problems on the warm-up. They are problems that you should know how to do. We're going to approach these two problems in two different ways today. We're going to look at them from the way that you've always done them, and then I'm going to show you a different way to look at them. Okay? So I'm going to give you guys a couple minutes while I put attendance in, and I'd like for you to go ahead and try these. They should look similar to ones you attempted on the homework. So use the slot diagrams if that's what's needed to be able to solve them, and we'll go from there. So if we look at the first problem, how we've done this type of problem thus far, up to this point, is using what strategy? Slots. I agree, a slot diagram. In this case, in number 1, how many slots are we going to draw? I'm missing Ricardo, too. Huh? 3. Perfect. Okay. And why 3? Because it says something about on the third try, okay? So we know that I might write that we were unsuccessful, so we failed the first time, we failed the second time, but on that third try, we were successful. We finally got that 5. Would you agree? Okay? So I'm going to put FFS, just meaning fail, fail, success. So what's the failure probability? 5, 6, because 5 out of the 6 times we are not successful. 5 out of the 6 times we are not successful. But then we get that 5, and so our last probability should be 1, 6. Good. Is it okay if I just write it in this notation? There's 2, 5, 6, and then there's 1, 1, 6. Does that make sense? Same thing, just a different notation, just mathematically writing it a little bit differently. Go ahead and tell me what that probability is. Tell me what you got. 0.1157. I agree. That's what I got too. Very good. 1157. Good. How is problem number 2 different? Katie? Yeah. So we're talking about within the first 3 tries, I've had a success. So in other words, I could look at it from this perspective, and I could say, good grief. Sorry. Okay. I could say I was successful on the first try, or I was not successful on the first try, but I was successful on the second try, or not successful, and then finally successful. Would you agree? Does that look right? So now I'm using slots again. It's just a matter of filling in with our probabilities. What was the success probability again? 1, 6. Good. And then our 5, 6. Good. We would call the first example just an exact situation. It's one time, we get that success on the third try. Number 2 is cumulative. Okay? It could have been the first or the second or the third. Go ahead and tell me what you get like this one. I'm going to do it a little differently. And I bet you I beat you. .4213. There is obviously a shortcut that I'm going to show you today, but double check that you get that exact same answer with the way I did it, or the way that we did it with the slots. Got it, Josh? Fernando, did you get the same thing? Still working? Did you get the same thing, .4213? You should have gotten it. Okay, great. We're going to revisit these using a different strategy at the end, or kind of like in the middle of class. Same exact problems, a little bit different way, but we'll get to that. What I'd like to talk about today is a geometric distribution. Okay, it is our second distribution in our probability distribution unit. We've already done binomials. Now we're doing geometrics. They're related. And then our last one is going to be normal that will start towards the end of class. But a geometric distribution is very similar to the binomial. The only difference is geometric, we are looking until we get the first success. Sometimes I call these wait time scenarios. How long until I roll that 5? I got the first 5 on the 3rd try. I got it within the first 3 tries. My first success, that's going to really kind of clue you in that we're talking about geometric distributions. Just like the binomial, there are in fact conditions to check. And actually, the first 3 conditions for the binomial are exactly the same for a geometric. So let's review what those are. Give me a condition. The trials are going to be independent. Very good. So I have trials that are independent of each other. Okay, give me something else. Go in. There are 2 outcomes, success-failure condition. I'd like for us not to get into the habit of doing this as our success-failure condition. I want you to be able to tell me what the successes and failures are. So be specific to the context of the problem. Okay? So I will just say that there are 2 outcomes here. But you would say, I either rolled a 5 or I did not roll a 5. And that's what you would check there. And how about the 3rd one? What kind of probability do we have to have? The same, okay? So we have the same probability of success for each trial. I can roll a 5 1/6 of the time on any given roll. Okay, good. So we'll come back to this formula here in just a second, but really what I wanted to talk about were these formulas. What does that little U with a tail mean? Anybody remember? It's the population mean. Sometimes we write that as expected value. Okay? And this formula, unfortunately, is not on your formula sheet. But you do need to know what it is. Okay? So it is one that's an unusual. Most of the time they're given to you, but this is one you'll need to memorize. It's pretty difficult. Lots of stuff involved. Yeah, it's hard. Can you remember that one? Just the expected value. We can do that. 1 divided by p. We can do that. That's not hard, right? That's not a hard one to memorize. 1 divided by p. And what is p again? The probability of success, okay? So if I asked you the question back when we were, let's take this idea. Oh, by the way, the standard deviation is not one I'll ever ask you to memorize. If I ever ask you for the standard deviation, I'll give you the formula when it comes to a geometric. Not binomial, because isn't the binomial one on your formula sheet? Okay. But the only one I would ask you to really know is the expected value off the top of your head. So let's take this formula for mean here, and let's see if it applies to this particular question that we did on the warm-up. Okay? So let's say the situation. I'm rolling a dice. I'm looking for how long, what, on average, how many rolls until I get the first 5. So that would be a question I would ask. Okay? On average, how many rolls until I get the first 5? So I need to check, is this a geometric situation? What are my conditions? Is it geometric? There's only 3, because a binomial, the 4th one had a set number of trials, right? So is this geometric? Number 1, what's the first condition? Independent. Does one roll of the dice affect another roll of the dice? They're independent, right? So we're going to say that they're independent rolls. What's the second condition? The success failure. So in this case, I either roll a 5 or I don't. So I roll a 5 or I don't roll a 5. Okay. How about the next one? The same probability. And what is that? 1 out of 6. Good. So is it geometric? Yes. Good. So that means that I can use the formula. I've checked the conditions. I can use the formula. Okay. So what is it? What am I going to do? On average, the mean is going to be 1 divided by 1/6. So what is that? 6. So on average, I'm going to have to roll the dice 6 times in order to get a 5. On average, I might get it the first time. I might get it the second time. But over the course of the run, if I did it so many trials, the average would be 6. Okay. What would make this a binomial situation? Because remember, binomial has 4 different outcomes, or 4 different conditions. What condition is missing? The number of trials. So how could I reword the question, this average question, to make it a binomial situation? Because that would be a different formula, because the average formula is different for binomial versus geometric. Anyone? If I roll the dice 6 times, on average, how many 5s would you expect to get? Isn't that different? Isn't that a different question? So if you're given a set number of rolls, now we're talking about binomial. Okay? So that's really what your goal is to decide, going through your checklist, is it binomial or is it geometric? Because they have different formulas, okay, for mean and standard deviation. Okay, good. So let's try a situation. Okay, so here's another example. Did you know that 8% of males are colorblind? Anyone in here colorblind? Or at least know that they're colorblind? My husband didn't know he was colorblind until he married me. I had to help dress the poor man. Y'all are too young for granimals. Anyone know what granimals are? Yeah, that's something from the 80s. Okay, that's fine. But back, why am I recording this? Okay, hang on. So a researcher wants to find some colorblind subjects and begins checking some potential subjects. What do you think about number 1? On average. On average is a clue. It stirs some things up in my mind. I'm thinking, ooh, that means a formula of some kind. Before I can use a formula, what do I need to do first? Not yet. Before I can even use a formula, check those conditions. I have to decide, is it geometric or binomial? Okay, so I've got to make that decision because there's 2 formulas to choose from. So let's do that. We'll see if there's a 4th condition. I'm not sure. So on average, how many men should the researcher expect to check to find one who's colorblind? That, to me, how many until, leads me to think it's which one? Geometric. That's usually a geometric situation. How many until? So I'm thinking geometric. So I'm going to check these 3 conditions. First one is independent. Now, we have to be careful with this one. Are the trials independent? When would they not be in this case? Family, because colorblindness is a hereditary situation. So it's possible that if I find one colorblind person, that I could test everyone in their family and they could be colorblind as well. So I have to be careful. Anybody reading the book about something called the 10% condition? Okay. The 10% condition is used when you can't be sure about independence. With the rolls of the dice, we can be 100% sure, right? We know that those trials are independent. Here it's a little not so sure. So what did the book say, for those of you that read it, about the 10% condition? Something about the sample size, right? The population has to, well, it has to be less than 10% of the population, right? So however many we check has to be less than 10%. Is it? The population of males is a lot. Would you agree? So I'm not going to, I don't know. I'm throwing a number out here. Let's say that in the United States there are 150 million males. What's 10% of that? More than I could try to get in touch with. Would you agree? So the people I'm going to talk to is going to be guaranteed less than 10%. Would you agree? Okay. So we're going to say that it satisfies the 10% condition. All right. How about so independence is okay? How about number 2? Okay, what are the successes and failures? Let's be specific. You're either colorblind or not. So you're colorblind or you're not colorblind. All right, what's the last one? So P is equal to 0.08, the same probability of success. Good. Is it geometric? Yay! It's geometric. Because it doesn't say, in the 50 males I checked, how many colorblinds on average would I expect to find? That's a different question. Here it just says, how many men should I talk to before I find a colorblind person? So this is our expected value formula. So what am I going to do? For us, what am I going to do? Okay? Good. And so what do I get when I divide those two things? I agree with you. What is 1 divided by 0.08? How many of these rascals am I going to have to talk to before I find a colorblind one? 12 and a half? Half? What, like no head? Or what is that? What do they mean? A young boy? It's on average. All averages, I expect them to have decimals. You should never round them to the nearest whole person. I know it's uncomfortable. I know it's weird. I know it makes you kind of creepy. But we are going to say 12.5. And I actually want to make sure that you're including units as well, okay? So you should say the word people. 12.5 what? Or men. It's actually men, isn't it? Shouldn't I say men, not people? Because I'm more concerned about the men. Because biologically, genetically, they're the ones that carry the trait, not women. We're off the hook for once. Always our fault. Anyway, number 2. What do you think? This is a different question. I'm going to pause the recording. I want you to read it, and let's figure out how to answer this one. This question is a little strange because, first of all, we're not worried about average, so we're not worried about the expected value formula. We still have a geometric situation, except we have no success yet. Do you agree? It's all failures. So this is really just kind of a slot diagram, like we've always kind of done. Okay? So among the first men she checks, I'm going to have 4 slots. I have no success. So isn't it just 0.92 to the 4th power? Would you agree with that? The 4 slots, they're all failures. All that means is that they can see. You're a failure because you can see. So 0.92 to the 4th, I agree. It doesn't quite become, we don't have to use the geometric formulas until we get that first success. Did you get that? That's what I got too. All right, let's try some more. These actually are going to be more of the geometric situation. But let's look at the third example, letter C. What's the probability that the first colorblind man will be found on the 6th person checked? Well, if we're thinking about it from a slot perspective, aren't the first 5 a failure? And then don't we get finally our first success on the 6th one? Isn't that really what's happening? I just didn't draw out the slots, but isn't that really the formula for it? That's what I meant to say. Thank you, Byron. Yes. It is. Now, let's look at this from the formula I provided to you for as an example. Okay? So if you look back at the formulas, this formula here, this qx minus 1, what's q again? 1 minus p. Isn't that where I got my 0.92 from? What is x minus 1? Well, 6 minus 1, well, wasn't that where the 5 came from? And then I have p. So it is the formula. It's what we know. It's what we've always done. It's just instead of writing slots, we're now just putting them together. That's all. No big thing. We can do this. Okay? Let's plug it in. Let's see what you get. 0.92 to the 5th power times 0.08, which is my first success, 0.0527. Would you agree? Awesome. I promise you, it's 0.0527. Sorry about that. All right. Letter D. What do you think? What's the probability that she finds someone who is colorblind before checking the 10th man? So, first of all, is it geometric? Why is it geometric? My first success happens at some point, right? Okay. Now, key words here is before checking the 10th man, which means I could have found it on the first man, or the second man, or the 3rd, or the 4th, or the 5th, or the 6th, or the 7th, or the 8th, or the 9th. What about the 10th? No. Before the 10th does not include the 10th. Would you agree? All right, go ahead. I'll tell you what the answer is. I'm not going to make you do that. Add all those together. Ms. Maggart will be here till, like, you know, the bell rings. I mean, you could do it. Wouldn't you agree? It would take a while. There's a shortcut, obviously. Okay? So what I want you to do is I want you to find your calculators, and I'm going to show you the shortcut. Okay? So go ahead and turn on your calculator. Well, without trying to, let's see if try to get it. Turn on your calculator. I know it can be done. There we go. Go ahead and go to distributions and find the geometric distributions. You'll see them, if you go to distributions, second bars, and scroll down, you'll see at the very last two are the geometric situations, or distributions. Just like with the binomial, there is a CDF and there is a PDF. Let's look at question C. We say that exactly on the 6-1, the sixth person that's checked, that's when our first success happened. So which one of those would that be? Be a PDF or a CDF? PDF. It's a probability density function because it's exactly on the 6-1. Remember how we talked about last class about the word exact with binomial? Same kind of situation here. So we're going to try that one by saying it's a PDF. What's the probability of success? Colorblind 0.08. And in this case, the x value is going to be, when does that success happen? 6. Paste. The notation is geomet PDF 0.08, 6. Guess what? Got the same answer. Okay? I want you to be able to recognize both. Now, when we come down here to the bottom, this last question where we're going to have to add a bunch of things together, what is that? That's going to be a CDF. That's a cumulative density function. Our probability of success is still 0.08. What's our x value here? 9. Very good. It is not 10 because it's before the 10th person. And you should get the same, or you don't get the same, you don't even know what the answer was before, but 0.5278. This one had a 0 in it, okay? 0.05. Thank you. Mr. Stafford? Mr. Stafford needs to see you. Okay? So I am okay with you using the geometric distribution function on the calculator. Just make sure you recognize which one it is, and you have to do your check. Okay? Is that all right? Let's go ahead and revisit the warm-up. Let's make sure, I just showed you the calculator. Let's look at the warm-up. Let's see if I could answer the question using the calculator here. A 6-sided dice is rolled. We're looking at that first one. What is the probability the first 5 is rolled on the 3rd try? Is it a PDF or a CDF situation? PDF, exactly on the 3rd one. So we're going to go here. We're going to go to the distribution. We're going to go to PDF. What's the probability of success from the warm-up? 1 out of 6, so 1 divided by 6. There we go. Doesn't like my fingers for some reason. What's the x value here? 3 on the 3rd try. I agree. And we should get the same answer that we got from the warm-up. And we do. How about down here, within the first 3 tries? Which one is that going to be? It's a CDF, still geometric. Maybe. Here we go. And then what am I going to put? Still my first success, or my probability of success is still 1 divided by 6. What's my x value here? Within 3 does include 3. Okay? So I'm going to say 3 here. Sometimes the wording, that's the hard part. I get 0.42. I think it's the same answer we got before, isn't it? So it's okay to use your calculator or slots. Either way will work. Or the formula. Okay? They give you the same answer. Good. So when you look at your textbook homework, okay, Question numbers 15 and 16 should make a little bit more sense now, okay? I think most of you probably did them with slot diagrams, but especially those question letter A, it was a question about on average. So those were the formulas you need to go back and look at. So part of your homework is going to be to go back and look at questions 15 through 20. Make sure that if you didn't know how to do them last time, you should be able to do them this time. Okay? Any questions? I'm not going to assign any more binomial or geometric questions until next Tuesday. And then you have your practice. Have I talked to you about the midterm exam at all? Okay, kind of. We're going to talk more in detail on Thursday. Please, on Thursday, bring all of the tests that you've taken thus far. I know I have the test for the test corrections still. And if I have some papers here, I'll hand those back to you either today or on Thursday. Byron, do you mind putting your phone away for me? Because I sure wouldn't be up here talking on my phone while I was, teaching you. Okay, good. Bring your tests with you, any that you can find, because remember how I said I'm going to be pulling the midterm exam questions from those tests, okay? So I want to make sure that you have all of them so you know what to study from. Fair enough? Bring them on Thursday. Next Monday, is a holiday. The Tuesday, I will be giving you questions on binomial, geometric, and what we're about to start normal, because we never took a test on that, but there's still going to be questions from the on the midterms. I feel like you're tested so much that I don't want to give you a test just on that and then give you a midterm. Like, to me, it just makes sense to put it on the midterm, but I will give you the questions ahead of time. Does that make sense? So I'm going to give you like a test bank of questions to choose from, but you're going to have to do the questions, right? I'll give those to you next Tuesday. Anyway, all right. We're going to do something you've done before. Something I know that you've all seen before. And that's exciting. I know Maria saw it because I taught Maria this. And I know Karen saw it and I know that Jennifer saw it and Corinne, because I all had you in Algebra 2. So I know you've seen it. Yes, sir. For the midterm, I wasn't planning on it because we're going to have some time in class. I was planning on at least one full day in class to review before you take it. That Monday, because isn't it going to be Wednesday, Friday as your midterm? I think I gave you the dates. No. I didn't give this class the dates yet. The last two classes of the semester are going to be your free response and multiple choice. I believe that's Wednesday and Friday. The last week in January, sweetheart. But that Monday, I'm going to be reviewing, okay? But on Friday, we'll talk more about which tests I'm pulling from, because I'm just in the process of writing it now. I haven't finished, and I'm keeping all of the tests I'm selecting from, so I can tell you which ones you'll have to look for. That'll be on Thursday. Okay, something that we've done, normal distributions. I even went so far, because I'm such a math nerd, but I love it, is for my Christmas tree this year, I ordered normal distribution ornaments. It's okay, I like them. I think they're cute. They have little smiley faces. Look at how cute they are. They're fun. So what do you know about normal distributions? Give me anything. Okay, yeah, they are Christmas ornaments, at least the ones in my hand. But what else? What do you remember about them? Something about standard deviation, absolutely. Okay, these little normal distributions have lines on them for a reason, and we'll investigate why that's true in a minute. Has something to do with standard deviation, I agree. Give me something else you remember. Yep. Ooh, that's good. The middle is the mean, I agree. It's also the median, it's also the mode, but it's definitely the mean. Okay, let's think back to the beginning of the year. What kind of shape does it have? It's not a word I ever used. It begins with an S. Symmetric. Isn't it symmetric? Definitely symmetric. How many modes does it have? So that would be unimodal. Remember these words back from September? Gotta be on your midterm. I hope you do. So it's symmetric, it's unimodal. What else do you remember?
Shows the percentages of the data that lies.
Yeah, so underneath this normal curve, and there's nobody in here taking calculus, right? Although some people take HL and statistics at the same time, so it happens, and I actually have somebody in my other class that's doing that. Integration under an area under a curve, anyway, it's beyond, it doesn't matter, I'm not going to talk about you. Anyway, they are related, but yes, the area underneath this normal curve gives us probabilities, and that's what we're going to talk about. And we're going to use the normal curve to find these probabilities, okay? Now, there are an infinite number of normal distributions, all kinds of them, okay? Some are really tall and thin, some are kind of short and flatter, but they all have some things in common. The things that they have in common is they are bell-shaped. I hate that word. I don't know why, but unimodal and symmetric is my preference. I'm going to write that. Statistics likes to say the words mound-shaped. I think those are the words I used before. I don't know why the College Board likes mound rather than bell. I don't know. I've never seen a bell that curves out like that and goes on forever, but mound-shaped, unimodal, and symmetric. Very true. Symmetric. The mean, median, and mode are all the same, and they actually happen to be in the middle of the graph. Okay, agreed? The mean does lie in the middle. These are all things we know. Nothing out of the ordinary yet. The mean, these are just, don't write all this down because this is just kind of common sense. The mean's always in the middle. The last two are some things that, we should probably emphasize. That tall, thin graphs are going to have a very small spread. And this is, again, just kind of a shout out to what we did back in September. We know that if the graph is squished in and thin, then the spread is small. If it's more flattened out and wider, the spread's going to be larger. So these are just things we know. We've seen this. We've heard this before. We're just kind of putting it all together now. Okay? So what I'd like us to do is I'd like us to be able to match some given normal distributions with some proposed mean and standard deviations, because we know that standard deviation is spread and that the mean is the measure of center. And again, this will be on School Fusion if you didn't get it written down. But if you look here, oops, it's got kind of big. Let me move these around. These are all, I'll kind of line them up here. These are all normal curves that are on the same scale. And I want us to be able to drag them to the correct place. Okay? Any volunteers? Anyone want to come up? Because if you don't volunteer, I'll volunteer you. Come on, Cameron. Anybody else? Just drag one to where you think it should go. Large mean, large standard deviation, small mean, small standard deviation. I don't know. Anybody else? Oh, drag the graph. There you go. Okay. All right. Anybody else want to try? Go ahead, Katie. Anybody else? Byron, I volunteer you. Anybody else? Karen, oh, Boris, you saved you. He saved you. Go ahead, Boris. Thank you. Let's see if we agree with all of their picks. Do you agree? Maybe. I tend to like the one that stands out the most, the real tall and thin one. Would you agree that it's located with the right mean and standard deviation? I would. It has the smallest standard deviation of 1.3. It also looks like the mean, or the middle, is far left, so it looks like it has the smallest mean as well. So I would agree with this pick here. Good. Looking at the other ones, okay, which one looks the flattest? First one. But I actually think it's in the correct place. Okay? Why? I'm going to try to, it might be harder to see if I line them up one exactly over the other. It might be a little easier to see. Why is lining them up? If I tell you they're to scale, why would that be important? Because it shows where the, not the spread necessarily, but it shows you definitely where the middle is. Would you agree? These two have approximately the same middle. The one at the bottom is definitely much more to the left. Would you agree? Doesn't that kind of equate to what I'm saying here? And that the mean of the last one should be 8. Would you agree? Because its middle is farther to the left. And then what about the top two? Which one looks more flat, the top one or the bottom one? So are they all placed correctly? I think so. Okay? So this mix and match and drag and drop could be something you'd see on your midterm. I can't guarantee it. I'm in the process of writing it, but do you think that seems like a reasonable thing? Not too hard, right? Okay, good. So let's talk about what Boris suggested in terms of standard deviation. He remembered that thing, and these little lines that are sewn so beautifully on my little ornaments. What the heck are they doing? What does that mean? Well, back in the olden days, like in the 1800s when I took math, just kidding, it was called the empirical rule. But some wise guy decided that name didn't quite fit. And we're going to change it to the 68, 95, 99.7 rule, because that just rolls off the tongue. Okay? I will never call it that, because that's a mouthful. The 68, 95, 99.7 rule. Don't you know? Come on, Lexi. Don't you know? Like, that to me just sounds hard. I know why they did it, because it corresponds to the percentages. That's fine. But that's also cheating. Okay, you should know them. But what am I talking about? 68% of the data lies within one standard deviation of the mean. So we're going to look at what that looks like in a minute. 95 fall within 2. So what I mean is this. Good Lord. Come on. If I was going to draw a normal distribution, okay? By the way, why does it, when it gets flat at the end, does it just stop? What's happening on either end of that normal curve? They go on forever and ever and ever. But what are they doing? Getting close to something. To the x-axis? Would you agree with that? To the flat? What do we call that when something kind of skims it but never quite touches it? An asymptote. So these actually become asymptotic on either end. Okay, they never actually touch the x-axis. They just kind of continue to get flatter and flatter all the way out. Okay? So what I mean is this. If I have a mean, one standard deviation on either side, where I add one standard deviation or I subtract one standard deviation, 68% of the data will lie here. That's what that says. If I go 2 standard deviations above, so here's my middle again, 1, 2 standard deviations above, or 2 standard deviations below, now I'm at 95% of the data. All right, go ahead. And if I go all the way out to 3 standard deviations, whether I add them or I subtract them, now I have 99.7% of the data. Almost all of it. Why not all of it? Again, it's getting asymptotic and very, very close, right? So very, very minuscule ports of are either side. If it's outside 3 standard deviations, that's unusual. And that's going to come into play on Friday or Thursday. When is it unusual? What does it mean to be unusual? All right. Let's try some problems here. Here's a much prettier picture. We'll refer back to this in a couple of minutes. Yeah, I don't know why that guy's there. All right. Let's look here. Can you read that? That looks really small to me. Yeah, it's small, but you can read it. Can you read it? Matthew, can you read it behind your eyelids? No? Okay. You feeling okay today? Any better today? So I wrote this problem back when Hummers were of the popular rage. Okay, remember those cars, those big Hummers? You ever like, some famous celebrities were like driving around with some crazy cars that were like half 18-wheeler, and I don't even know. It was making me angry because they just eat gas. Bad. But now we're a little bit more socially aware. We have hybrids and things, so that's fine. But just keep that in the back of your mind. When the numbers come up, you're going to be like, well, my car gets better gas mileage than that. I probably need to adjust the numbers, but that's okay. So fuel economy of cars in Manassas area, I'm telling you that they're normal. That's key. I have to be told that. On Thursday, we'll investigate how to prove something's normal or how to show that it's probably normal. But for now, we're being told that they're normal. You also need to be given a mean, and you need to be given a standard deviation. That's important, okay? Knowing that, I want us to draw a normal curve and show me 3 standard deviations above and below the mean. Can we do that? Let's try. Where do I start? The middle. Good. Jennifer, what's the mean? So I put 24 right in the middle. And I'm going to go up 1, 2, 3 standard deviations, and I'm going to go below 1, 2, and 3 standard deviations. I'm also going to attach numbers to those places. Excuse me. The standard deviation is 6. So I'm going to add 6 to the right, and I'm going to subtract 6 from the left. So what's 24 plus 6? So I have 30. And what's 30 plus 6? And then another 6, 42. Now, we know hybrids get more than 42 miles to the gallon. I get that. Pretend that this is pre-hybrid. Okay? Going backwards, 24 minus 6, 18. Minus another 6, minus another 6. Hummer. Are we okay with what I'm doing here? Just taking the mean and then just doing. Now, before the hybrid phase or craze, I can say that because I have one, so I know. All right? But it would be unusual to have a car that had below 6 miles to the gallon or above 42 miles to the gallon, okay? Because 99.7% of them should be within these two brackets, or 2 endpoints. Okay, so let's ask ourselves some questions here. What percent of the cars driven in the Manassas area get between 12 and 36 miles to the gallon? Huh? Where'd you get 95? You answered that awful quick. It's the rule, the empirical rule, right? So we know that the rule says between 12 and 36. And I actually always want you to draw it and shade it. Because as part of the rubrics for any AP question that I've seen on normal distributions, drawing it is part of the rubric. Okay? So I'd like for you to make sure you're including that. Also, one more thing, and I didn't tell Block 2 this morning. Shame on me, but they'll figure it out on Friday. So Thursday. Well, the book tells you too, but there's some notation with all of the distributions actually, binomial and geometric, and we'll go back to that. But if you just use the big capital N, that stands for that it's normal, and we can just say 24 and 6, and we are assuming that is the mean and standard deviation in that order. College Board tends to use this notation quite a bit. Okay? A capital B would stand for binomial. A capital G would be geometric. So just kind of be aware of that notation. Okay? So within 2 standard deviations, that's 95%, 1, 2, 1, 2. Smacker, that's not hard. All right, I'm going to try some different questions for you, though. Here's the first one. We're going to do several. What percent of the cars get above 30 miles to the gallon? What percent get between 12 and 42 miles to the gallon? What percent get below 24 miles to the gallon? what percent get above 42 miles to the gallon? All right. There is a shortcut on the calculator, because I know Matthew, when he was doing the distributions and we were looking at binomials, said, I see normal CDF, Ms. Maggart. I see it. You saw it. Yeah, sure. You saw it. We'll do it on Thursday. For now, we're going to use the empirical rule. It's okay. It's not hard. It's not good. So how would I use the empirical rule here? Let's make sure that we're drawing the picture correctly. So I'd like to do that in each of these cases. I am going to be expecting a normal curve. So I have 24, and I have 30, and I'm looking for above 30. So you should draw. So when I pause the recording for a minute, take a second, draw all of, shade what you're looking for, and let's see if we can't use the empirical rule to come up with some answers. I know we can.